All right. Can everyone hear me? Oh yeah. Okay. Cool. Hi everyone. I'm incredibly sorry. I had some issues with my internet, so I was unable to join in time. Uh, However, we are able to begin. So one second. I need to figure out how to make okay, switch on presenter mode for the speaker. Okay, that should be good now. And yeah, so good morning to everyone. My name is Jubilee Itunji. Thank you for joining our second meetup. Today we have Oguna, aka OG, aka Senior DevOps Engineer, with us today, and we'll be talking about how cluster autoscalers enable anti-fragility. If you're not familiar with cluster autoscalers, this is the session where we'll be going through what they are, what they do, and of course, like how anti-fragility is like relevant to your production deployments. So without wasting too much time, I'll be passing the mic to Uji to take us through it. And again, incredibly sorry for the delay in starting. But yeah, we can move on now. Uji, the floor is yours. Hopefully,
Guys, can everyone hear me?
we can hear you okay.
Okay. Um, Good morning, everyone. So apologies for joining late. Not joining late, ready for starting late. Actually, trying to sort his internet. So let me quickly share my screen. Just let me know when you can see my screen. With a thumbs up or you know. Okay. All right. So I will be sharing my screen. All right. A thumbs up if you can see my screen.
Yep, can see your screen just fine.
All right. So good morning, everyone. The name is Ogonna. The name is Ogonna Namani. I'm a senior DevOps engineer. I've been for a little over 4 or 5 years now. And yeah, I'll be talking about cluster autoscaler and how it enables fragility, anti-fragility rather. So this is Kubernetes heavy a bit. This is so if you have prior experience to Kubernetes, maybe not so much experience, but like a little experience to go by, at least understanding the basics. I don't think this would be so far from you. This would be something that you would relate to, you relate to very well, and could help you when setting up, scaling in your clusters, deployment clusters to be precise. So this is what our agenda is going to be like today. What is anti-fragility, resilience? We're going to talk about the difference between resilience and anti-fragility. Then we'll talk about what a cluster autoscaler is in the first place, right? What does it do? Why is it needed? Why was there a need for it in the first place? And then we'll talk about the difference between the Kubernetes native cluster autoscaler and then Carpenter, which is a I would say an EKS, an AWS. It was first made by AWS, and then Azure adopted it as well. I think it's yet to get stable for GCP, but it's also a cluster. It's a cluster autoscaler. So I'll be talking about the difference between the native traditional Kubernetes autoscaler and Carpenter. And then we're going to go a little bit into Carpenter and how how the self-healing architecture works and how you can, leverage this in your deployments. And then we'll have like a little demo just to show how this works in real time. And then we'll have some questions. So let me begin. All right, so I'm going to start with what anti-fragility is in the first place. What does it even mean? So this is a concept introduced by someone called Nassim Nicholas Taleb in one of his books, Anti-Fragile: Things That Gain from Disorder. So basically, this was not referring to anything tech. This was him referring to happenings, systems, not just infrastructure, but like happenings in life in general, businesses, everything, other aspects of life you can think of. So the concept of anti-fragility in general is not new to everyday life. This is something we experience in something as trivial as going to the gym, right? The muscles, the human muscles, you gain muscles by working by working those muscles out, right? By lifting weights and doing some exercises to focus on some particular muscle clusters, right? So that is an example of a system or a body part, for example, that gains from stress or disorder. So if we're trying to narrow that down into DevOps, we're going to do it in DevOps or systems design in general. So if implementing anti-fragility, you're going to talk about the exact difference of fragile. So fragility is something that is fragile. The exact opposite is anti-fragile. Not opposite, I would say, not opposite, but for lack of a better word, opposite. So it means building systems that not just fail, but fail and learn from those failures. So this does not mean that you're not going to fail. According to AWS, everything fails, right? And that's how we build backwards. So anti-fragility in DevOps is basically, or systems design is implementing with that mindset that this thing is going to fail, and at some point when it fails, I should be able to learn from that failure and improve on whatever that I'm building on. So that's why I said it means building with a mindset or system that encourages room for improvement and growth. So resilience. Um, what is resilience? Resilience refers to the ability of a system or entity to withstand shock, recover from adversity, return to its original state of function. It suggests the capacity to absorb and adapt to challenges without significant damage. So when you have a resilient architecture, basically what this is saying is you have a very good architecture. You have something that you rarely have downtime, and even when you do, you are going to be available to fix it, regardless of what that is. So this is what resilience is. This is what a resilient architecture would be basically. So I have a little diagram here that shows what happens, what happens to resilient environment or resilient system. So let's say you have an application, your system is stable. I would say if there is something as a resilient chart, it's at 70%, right? Let's say it's a very good environment. You have your scaling, you have security, everything, right? It's at 70%. I mean, there's room for improvement, right? And then something happens. You get a downtime, someone pushes something, DNS, anything, you recover. So let's say you have you have a system, and then for some reason a new team pushes a new image, and for example that new image is using a platform AMD. Meanwhile your previous images are ARM, for example, right? And then you, for your, what's it called, in your node affinity, in your pod, in your deployment file, your specifications are pointing to, or are rather restricting the pods that spin up to be AMD, to be ARM, right? So what happens is that you're going to have a lot of pods that are going to be unschedulable just because you have something blocking or restricting them from being scheduled to that particular node. Now, when you see that this happens, so let's say this is the situation and you have a downtime. When this happens, you immediately go there, create a new file, add a new rule, allow this particular guy, and then you recover. But then your environment is still at 70%, meaning that if this happens again tomorrow, you will have to manually fix this again, right? Now let's go to anti-fragility. Anti-fragility goes a step beyond resilience. You're not just withstanding or absorbing this stress, you are looking at it as a means to benefit and improve your system, right? So the more problems you have, so I'm sure that most of us have heard about chaos engineering. There are companies, very big companies, especially in finance and trading, all those the finance trading, the stock market. There are some businesses that actually chaos engineer their environment. They, for lack of a better word, they try to break or spoil something every now and then just to see how quickly they recover. I've forgotten one of them, the name of one of example of that company. It's on this AWS YouTube playlist called This is My Architecture. I think that's the name. So there are several companies there, even Snapchat, just talking about their infrastructure and how they leverage AWS. So there's this company that that's disabled an availability zone every 24 hours and try to terminate 17 instances. There's a lot of stuff to just see how quickly they recover from very unseen or situations that they don't even predict, that can happen. Shutting down a subnet, changing a rule, something like that. Just see how quickly that they recover from those particular things. So chaos engineering is a step above building. You can build something good and you can't know everything. That's where you keep the room for the unknown unknowns, things that we do not know that we do not know. You can never see all the parts, you can never see all the angles, and you know that's just it. So this is the same example, but for an anti-fragile environment. So you're at 70%, you have a downtime, you experience that downtime, you recover from that downtime. But now you're not just recovering from, okay, yeah, I think Jibril has posted that link on the chat for for Snapchat. So that's just an example. So you have that exact situation for an anti-fragile environment. You have a downtime, but now you're not just manually going to fix something. After that is done, after writing your post-mortem, you are taking notes from this. You are creating tickets that are going to fix these problems immediately. You're trying to automate the process. You're keeping room for this occurrence in the future, just in case this happens again. Right. So there is something we call the second order derivative. So this is a term I borrowed from physics and mathematics. So if you forgive that I said I borrowed it from physics and mathematics, those are not my favorite subjects. They never have been. But I saw this as a very important mindset or term or something to relate to system design and infrastructure provisioning in general and management as something that we could relate. So, what is a second order derivative? In plain, simple layman terms, it just means that when something happens, something else is going to happen, right? One plus one is one. One plus two plus two is going to one plus one is two. Two plus two is going to be four. You see, I said one plus one is one. So terrible. Forgive me, guys. So yeah, so what it means is when this happens, something else is going to happen. So let's say you provision an environment, you put your auto scaling group, you're expecting traffic. Expectation, that is the second order derivative. For everything you're working on, you should ask yourself, now I have this, what next? Right? So in this write-up, you see I said it's how fast system behavior changes in response to any event specifically, whether it degrades, stabilizes, or improves when pushed beyond its first reaction. So what happens after the first reaction? You set up your environment, you set up the auto scaling, all of that good stuff, your security as well, and then you get hacked, or then you expect traffic and traffic comes. What next? What happens to your environment? Maybe you only applied auto scaling to the compute and not your databases, or not to your, maybe you have a proxy somewhere that is helping to do something. Maybe there's a queue somewhere, and that queue is not a managed queue. Maybe it's just a Kafka stream, and you didn't provision that traffic there at that point to actually scale. You just focused on, oh, when traffic comes, scale. Like your service is scaling, but the bottleneck, the microservices, the queues, for example, if you're using message brokers, those queues are going to be clogged because you didn't give room for concurrency at that particular stage, right? So it's not a bad thing to miss these things, right? Those are the things that make us better engineers. But then expecting the second order derivative, if you can, is a very good step or bold step towards heading to the anti-fragility journey in, setting up a very stable and steady environment. All right, so I'm going to move into Kubernetes scaling in general, right? So I'm not talking about the anti-fragility and what it means, and now we're going to narrow it down to Kubernetes and how Kubernetes handles that in form of scaling. So we have different methods of auto scaling in Kubernetes. Kubernetes as it is a tad bit complex. It's, when they say you try to solve a problem, most of the time you solve a problem by creating a new problem. And that's just how infrastructure, know, DevOps, systems design, that is literally what we do every day. You're having a problem, you split your services into, you split your system from monolith to microservices. For every new layer you introduce, or every system or any step or layer you introduce to your environment, you have introduced a new layer of complexity to that environment. So Kubernetes is, it does a lot of things, but also gets it that big complex. Now, there are different ways that Kubernetes handles scaling. So we have the HPA, horizontal pod auto scaling. This is where you have a pod handling a request, and you set some rules, CPU and memory, and then Kubernetes tracks those metrics. And when you are above those thresholds, let's say you set the CPU at 80 or 70. So when your CPU for that pod is above 70%, Kubernetes is alerted, and then a new pod is created from that pod, and then a new avenue has been created for your service to be, your traffic to be served. So that's basically horizontal, so creating a new one. And then vertical is just same we have with the compute, but now you're not creating new pods, you're just scaling the pod upwards. So you're just increasing the size of that pod to fit your purpose. Now we have, so this is on the pod layer, right? You have the nodes, you have the pods. So fine, the nodes are scaling fine. You have your HPA, everything is fine, it's business as usual. But now those nodes run in a cluster. How do you manage those clusters? Because if a cluster node is on AWS, if it's a T3 medium, that's at best 2 vCPU and 4 gig of RAM. I'm not very sure. That's like the average of what you're going to get. If it's a M instance type, that's what you're going to get around that size. Now, if you have requests of traffic that is requesting for 4 or 8 vCPU or stuff like that, you're going to have to increase that node that is running those pods inside. So that's where it gets tricky. You need to also handle scaling on the cluster level, not just on the pod level. So there's something called a managed node group. And according to several cloud providers, they handle it separately. I think it's in the next slide. All right, so I'll just start with this. So okay, let me just begin with this. So Kubernetes introduced the Kubernetes cluster autoscaler, which is a component in Kubernetes that adjusts the size of clusters so that all pods will have a place to run, by ensuring all pending pods are scheduled. So basically, how this happens behind the scene is Kubernetes is steadily pulling an endpoint, pulling your job endpoint. If a new pod comes and that pod is unschedulable, Kubernetes would look at your autoscaler. If you have some rules there, it will use those rules to provision new nodes for you, depending on the rules you have configured for your scaling to happen. So that's it's in very simple English. That's what the cluster autoscaler does, right? It's checking for pods that are unschedulable. If your pod is unschedulable, most of the time you is because there is no space to schedule that pod, or a rule or two is blocking that pod. So Kubernetes goes for those pods and tries to schedule them on a node. And when there is no node to schedule those pods, it's going to try to create a new one depending on your config settings. Now, this is available on our popular public cloud providers, so AWS, GCP, and Azure. And how this works is when you create your node, you have like an autoscaler. Because at the end of the day, these nodes are running on compute resources. So for AWS, your nodes are literally your EC2 instances. or if you're using Fargate, except you're using Fargate. But if you're using like if you're using an EC2 mode, you're literally having compute, you're literally having EC2 instances. So your T2 micro, T2 nano, all of those, your CL, all of those is literally the nodes you're going to have. It's not something else, it's not something abstract. You're having just EC2 instances, compute resources. So how do these compute resources scale? They scale by auto-scaling groups, managed instance groups for GCP or VMSS for sure. So if you're using any of this cloud provider, this is how your native Kubernetes cluster autoscaler is going to work. So you're going to define an autoscaling group, and when Kubernetes goes there to see that it needs a new pod, it's going to hit your it's going it's going to go to your config, and then from your config, it's going to hit the manage node group, and then provision, then call the EC2 API or the VM, the compute instance API to create a new node from there. Okay. All right. So I'm just going to. So I think I duplicated that. All right. So I'm just going to go into um, the obvious difference between this and Carpenter. Hold on a second. I think I missed somewhere. All right, so I think I missed one page. So I'll before I get into this, I'm going to talk about Carpenter a bit. So Carpenter is a type of cluster autoscaler. I think it was created by AWS 4 years ago. I think not very sure, but currently it's managed by the Linux group, so it's open source, and it was made by AWS, so it works better or works well or started working well with AWS. So basically, what I said earlier about your your traditional Kubernetes cluster autoscaler that goes to read from an auto scaling group, then calls the API, then calls the node group before it gives you a new node. This can take minutes before that happens. So what Carpenter does, or why people even use it, or why it's even a thing, or why AWS even why it's a thing in the first place, right? It's because the speed at which this guy gives you these pods or these nodes rather is very fast. Something that your cluster autoscaler that will take your cluster autoscaler 5 to 10 minutes, Carpenter will do it in a minute or two, less than a minute most of the time because it's very fast. Now, why is it this fast? So Carpenter, what it does, right, is simple layman English again. What Carpenter does is it removes all the complexities in between. It doesn't need an auto scaling group, it doesn't need a managed node group. Just define your node class and your node pool. Carpenter is going to go there, call your EC2 API. As long as it sees it has the same process, right? It's pulling and looking for pods that are unschedulable, right? This pod, okay, let's try to schedule this pod. If you can't schedule that pod somewhere, there's not enough capacity, it immediately uses the node group to call the EC2 API, right? It's calling the API to give me a new node of this size in this zone with this capacity immediately. Now, this node starts provisioning. Now, all these processes of going to the auto scaling group to check how many you need, it has jumped all those processes. So that's exactly one of the, I would say, selling points, one of the things that made Carpenter or that makes Carpenter very, very exquisite. And people love to use it, especially within the AWS ecosystem and Azure now as well. So one of the major differences, latency. So just exactly what I said, when that's cluster autoscaler sees pending non-schedulable pods, it relies on predefined scaling config, example, scaling group or MIG, which in turn relies on calling the node pool specified before interacting with the API. So you see that there's a long chain of command before the cluster autoscaler carries out this scaling. Now, for Carpenter, we see that it has boycotted, or rather left all of these guys. It just needs a rule here, and then it just goes, once it sees this pod, it goes straight and calls this guy, and in seconds you have a new. mm, mm, okay. All right, so we have node flexibility. So another advantage of cluster autoscaler of the carpenter across above cluster autoscaler is node flexibility. Now, I mentioned a managed node group. A managed node group is node group is basically, if you want to configure that, or an auto scaling group, you have to say, for example, I want a T2 medium. Your node group is going to have, or your auto scaling group is going to have T2 medium, and that's what that group is going to have. So you're going to end up having several node groups across several files, right? What exactly, how is that a problem? Right? That is a lot of, so I mean, if you have 4 to 5 files managing just your managed instance group, it's already a lot of work to do. And let's say you have several types of like workload. You have like heavy workloads, you have AI workloads, you have compute heavy workloads that need a lot of compute resources. You're not going to use a T class for that. For example, you need something on the C side that has a lot of compute juice for you to carry out that particular task. Now, that is an example of what you do if you're using the Kubernetes autoscaler, the cluster autoscaler. Now you're going to have several node groups, and then you're going to have to manage all those node groups depending on what you want. Now, for Carpenter just needs a node class and a node pool. Now, what do they do? This node pool just determine. It says, okay, you know what? I want I want between a C, I want an M or a T. So depending on the workload you see coming, depending on the amount of request of CPU this job is coming with, give me give me a suitable pod or a suitable node for this particular workload. Now you see that you have a lot of choices. You're not constricted, or you're not boxed into one particular file. For example, you have these files in, how do I put it? You have you have options basically. You have options. Basically, you have a lot of options you can do. So I'm going to show us a lot of this, so much of this, when I get to the demo side, and also show you the files and how flexible you can be with using Carpenter. You can even select like the zones you want them to run. You can select the type of instances, the generation of the instance, the capacity type, the topology. There's so many things you can define with Carpenter that is very nice. So instead of having several files, you have one file, and that file is going to serve your needs. Now, Carpenter is smart enough to see your job and see the amount of resource that job is requesting for, and create a suitable server or node rather for that particular workload. Now, it's let's go to Carpenter's self-healing architecture. Now, this is an example of what your classic node pool will look like in Carpenter, your Carpenter node pool. Now, basically, what this node pool is specifying for this one, this is a multi-AZ architecture. Let's say you want to have a multi-AZ architecture. You want to have resources across all these regions, right? You have across US is 1A, 1B, 1C. These are availability zones. You can go as far as regions as well. Seeing what happened to US East One some weeks ago. If you had Carpenter that has like that's spanning across several regions, what will happen is that when Carpenter sees that this node, this particular zone is not responding, it will just continue sending to the other ones. It will just take those ports and route them to the other side without you even knowing. Maybe if you set some alert, you may know, but that's like about it. So we're seeing that we have several level of granularity. We have the topology. Sorry. We have the topology, which is specifying the zones you want them in. We have the capacity type. So do you want the spot or on demand? So this is something that I don't know if you can see my screen clearly. Can you see? Can I get like a thumbs up or something? No, you're just seeing my screen.
I can
Can
see
people
clearly.
react? Okay, you can see clearly. Okay, okay.
Yeah.
Okay, nice, nice. So we see here that we have the ability to choose between spot instances and on-demand instances. Now you see, now what this is basically is what this does for you is that most of the time when you're in a company, right, except you're doing a project, even for a personal project, cost is the first thing. Some people will tell you, okay, they know you can do this thing. We know you can do this thing, right? We know you can do it. But how do you reduce our cost? We are bleeding, right? So most of the time, your skill becomes everybody can do it, but how better can you actually improve our cost? Now, seeing that you can do spot and on demand at the same time, or even restricted to spot depending on your type of workload, even explains how granular we can get with Carpenter, which is very, very nice if you ask me. Because if there are no spot instances, for example, it can go to on demand. If your spot instances get disrupted or get reclaimed, an on demand node can be scheduled that will pick up that job and run that job for you and terminate as soon as you're done. Now we have spot instance fallback mechanism, just like I said. So this is another example of a node pool, but here we're seeing in this order, try the spot instance first before you try the on-demand. So we have an instance category flag as well, or parameter, where you can select what type of instance group. So instead of saying T3 medium or M2 X large, you're just giving it a group. Choose from any of these depending on my request of that particular job, the request and the limit, the CPU request and the memory request of that particular workload. Give me something suitable to handle that workload. Now, this instant generation, this is just it's just something fancy if you want higher speed, the newer machines. Basically, that's what generation means. Zone, this is exactly what we also mentioned. So I think we have talked about this as well. Okay, this is cost optimization. All right. So yes, you can see at instance size. With instance size flag, you can go as low as specifying the exact type that you want. Yeah, I think we've talked about cost as well. So now we are going to get to demo. But before I get to demo, okay, there's a question here. Is the autoscaler, which of the autoscaler, is it Carpenter or the traditional Kubernetes cluster autoscaler? Can you specify? So I think you're referring to what's it called? Sorry. Trying to set up the demo. Give me a second.
While you're setting up the mic, I actually answer that. Cluster Autoscale is kind of like a plugin for Kubernetes, right? So each company or whoever wants to implement the cluster autoscaler can then go in and then make a specific implementation, like how AWS did Carpenter. For the longest time, Carpenter only supported AWS, but right now that is expanding, right? And then there's the traditional what's it called, cluster autoscaler. So it's kind of an add-on is the better word, not like it ships with all providers. So I hope that answers your question.
Yeah, so just like Jube said, it's in the if you're asking if it's in the controller, yeah. So it's something you can add on to your controller and then it works like a component in your cluster. So it just so it's able to find the pods that are not able to be scheduled and then schedule them across. So you can enable it and use it as much as you like. Whereas an add-on and it's allowed across all right. So I'm going to share my other screen now. Sorry, I hope that answered your question. Let me go back to the chat. I hope that answered your question. Let me go back to the chat. Okay, okay, yes. All right. All right. Let me keep this screen here. All right, so what I'm going to do, I've already installed Carpenter. I've already installed Carpenter on my EKS cluster just because of time. So what I'm going to show, okay, I think I'll share this entire screen. Let me know if you can see my screen. Boom. I don't know if you can see my screen. So it's small. I'm going to zoom in on them individually just so you can see. So let me get like a thumbs up. If I'll share it, I'll start from the first one, and then I would let me share from the first one first. Let me share this window of my code before I. So basically, this is what I have. So I have a demo instruction here. What I'm going to do here is literally create. So I'm going to create a node pool. So this is my node pool. I call this spot node pool. It has a node class as well. So you can see this node pool. The name is spot demo. I'm telling it to create only spot instances, to use the platform that's arc of AMD only, and to only choose from T. You know what? Let me make this to choose from C as well. So let's just give it an option, right? So I'm telling it to span across these two subnets, these two availability zones rather. I have tagged, so with Carpenter, when you create a node pool or when you install Carpenter in your cluster, you need to give it permissions to provision. So you have to tag some subnets in the discovery here with this, so that whenever this guy is looking for, so it's called a subnet selector. So you need to tag those subnets explicitly and tell it, hey, provision on these specific zones, and then it's going to have permission to do that. So we have that, we have the default. So it's going to referencing to a node class. So it needs the node class. So the node pool handles the specifics, the core specifics of what this carpenter should do. Meanwhile, the node class is handling things like you're seeing the roles, the permission sets in need, the subnet in needs, the AMI type, so the image type that it should provision in the nodes. So this is more like an infra level, for lack of a better word, and this is a little bit more. The pool is more granular, but the class is more like use this to run this, so they go hand in hand. It was provided before, but then I think last year AWS like broke them down into node pool and node class. That way you have a little bit more flexibility as well. So I'm saying I want images from 2023 Linux, and then this is the name of my role that I've already pre-created. And yeah, so I'm going to run my commands and apply. The first thing I'm going to do is to apply this pool. I'm going to apply this guy. So let me switch back to the double screen so you can see this reflecting in the AWS environment. All right, so I'm going to go to my demo instructions that I have here. Don't need all of this. First thing I will do apply is to apply my node pool. So I'm going to apply this guy. So when I apply this file, because I have them as one file, and this is the name, what I'm going to have is a node pool and a node class created as a custom resource in the AWS environment. So if you come to the custom resource here, let me zoom into this side a bit so you can also see what's going on here. So from the terminal, this guy is still creating. So at the end of the day, I'm going to have a node pool and a node class. It's taking time. Don't know if it's network. Let me run it again. All right, so it's been created, as we can see. If you come to the right here, you're going to see we have created node pool and a node class. There's a node class. Yeah, this is it, the node class. So this is it. It will show here as the custom resource. If you run kubectl get node pools and get class, the name is default. You're going to see that this has been created. So we see that this guy's the node pool and the node class has been created. Now I'm going to go ahead to run this file. I have a file here called spot demo nginx deployment. So basically what this file is, let me open it boldly so everyone can see it. So it's just a simple nginx deployment, and I'm telling it to, this is my node selector. So I'm actually giving it a node selector. So you use a node selector when you want to restrict your deployment to a particular node. For when you have like several environments, you want to actually restrict your workload so you know where to save costs and what to shut down when. So I'm giving it a node selector and I'm pointing it to the Carpenter node pool, which I've created called Spot Demo. I'm giving it a topology, telling it to, if it doesn't fit or satisfy this thing, it should not schedule, meaning that it should only schedule in 1A and 1B, as I earlier said. And yeah, these are just the match labels, and then this is the CPU request limit. This is the image. So just a very basic file. So I'm going to go ahead to apply that now. And I have how many replicas? Let me see. I have just four replicas. Now let's go to the right here and look at workloads and go to pods. Now let's refresh. Let's refresh. We are going to see we have some pods that are pending, four new pods that are pending. If you run kubectl gets PO, let's get the pods in the default namespace. We see that they are still pending. You see on the right here, they are pending. If I keep refreshing, now how do we okay, now they are running, right? We have two running, and let's check it again. kubectl get PO. Let's see if they're running. Okay, one has. Okay, let's just do a wait and monitor this guy. All right, everything is up, everything is running. We have a 1/1 on all of these guys. Now, how are we sure? Okay, now I'm going to go to the instances, right? I'm going to go to the EC2 instances because we are using, obviously what we are provisioning are EC2 instances. Now, I ran this guy and I told it to give me 1A and 1B. Now, look, immediately I provisioned this guy. I have two new pods here. They are still initializing, but we have our guys already running to show how quick this was. So we see, if you go to the zones, you see one is at 1A, one is at 1B. So it has applied the topology that we applied earlier, telling it to have it across these two availability zones. Now I'm going to do, give me a second. I'm going to change this replication now to, let's say we have a spike and we have 25. Let's turn this to 25, right? We need 25 replicas. I'm going to apply this guy again, and we're going to see what's going to happen. Now I'm going to, let's keep this guy to wait, and then we'll start refreshing. So this is a minute ago, right? This is less than some seconds. I clicked on apply. We have two, we have four. How many do we have coming up? So this one here is the carpenter, manager. This is a managed node that runs the actual carpenter. So these ones are the ones that are provisioned. So you see here we have two new pods, and because it's seen that it needs 25, it's not going ahead to do T2 medium. It has gone to choose a larger one that would contain all the impending port or traffic that we have. So I've seen the T3 2x large, a T3 2x large in two places. So instead of having several T2 mediums, it has given us a compatible, because we specify we want it across a T. Wait, that's the node pool. We specify we want it across a T, a C, and a T. So it's giving us T because this is not a compute heavy workload. So it's going for, yeah, and yeah, it's creates a larger one, and it's also very fast. So this is how many minutes ago that how many seconds ago that we clicked on this. Let me just do a kubectl get ports, and we're going to see how quickly this guy would get our environment up running with 25 ports. Everything here is a 1/1 in less than a minute plus. less than a minute plus. Now it has shut down the other T2 medium and replaced them with these two. So instead of having that initial T2 medium, it's smart enough to also give us a better, it's smart enough now to also give us a better size for our workload, which is, I mean, is also what we are looking for. Now, let's say we don't want this in, let's say we remove the, what change should I do here now? You know what? Let me remove the T and tell it to only give me compute. If I tell this guy to give me only only C type instance, if I come here and apply this, we're going to see what's going to happen. So I've just applied this guy. So the what made Carpenter very popular across those AWS workloads is the speed at which you recover from downtime. Imagine this is a production environment. You're going to start serving traffic in no time. So I'd apply that I want only, okay, no. This is the node pool. So I have to apply the node pool again. So let me apply the node pool now. All right. All right, I've applied the node pool. All right, so let's see. So I'll just keep refreshing this so we see this in real time. Also on the AWS environment here, if you go to the namespace, let's go to default namespace. We're going to see all our guys. They are healthy, they are happy. I don't know if they're happy, but they are healthy and they are running. We don't know about their happiness. So now go to instances and let's keep refreshing to see what's going to happen. Now we just told this guy immediately that we don't want a T class, we want a C class. Immediately it has provisioned the C7i flex. It's such a long name, .2x large, right? It has created a new one immediately, still initializing as you can see. And if you do, if you go to here, you're going to see that these nodes are, let's go to nodes. We're going to see how quickly it's going to switch. You might not even notice this is it a few seconds ago and it's ready. Now all the workloads are going to be transferred to this guy. It's going to drain them slowly to avoid downtime. Now let's refresh here. You see it has started to terminate this it started to shut down this T3 2x large and this other one and moving all the workloads to this place. It's very fast actually. So the speed is the selling point amongst other things. Now, if we go ahead to delete, for example, if I delete or untag a subnet and say don't provision on this subnet, that's us simulating a downtime in that particular availability zone. What is going to happen is the same way that you had all these guys transferring to a larger instance or a C class instance. What's going to happen is it's going to take all that traffic, create more nodes on the particular zone that is seen that has traffic, and then transfer all that workload to that place very, very quickly. We see our guys are running. It has tried to shut down the T class guys very, very quickly. This is less than 3 minutes ago that I applied this guy, and we already have this. But if you've worked with cluster autoscaler, you will know how slowly it takes before this. I mean, we would have still been in the first instance where I'm trying to spin up the nodes because it takes quite some time. So yeah, this is it. And let's say the nodes come down to 4, as we had 4, our workload has gone down to 4, and I apply this guy again. It is going to find a very small pod, immediately reduce everything, drain the rest, and give me something that I need as quickly as I want it. So let me refresh this. Refresh this here. So we're also seeing how quickly things change because, like I said, compounded amount of nodes created. So it's specified here. The amount of nodes to be created, you can limit it. In a second. The amount of nodes to be created literally depends on the amount of replicas or the amount of jobs that you have coming. You can specify it in the YAML as well, but most of the time it just takes from what you have and finds a way to optimize it. But yeah, you can specify it here as well. You can specify it here as well. In a second. You can specify it in the node pool, the amount of nodes you want running. You can specify it in node pool here, the amount of nodes you want to spin, regardless of what, forgotten what that class is called. Let me quickly check what it's called. But I know you can specify it in the YAML. Carpenter, let me check documentation. Carpenter, node pool, plus limit. Let's see. So I'm going to just share another screen quickly, and then you will see. Just did a quick search. I just did a quick search here. Just did a quick search here, and you see you can have this guy. You can have this. So you can limit it by the CPU and the memory, right? And then it doesn't go past any of this. So that's an example of how you can limit it as well. So yeah, I hope that answered your question. Yeah. So, so, so as we can see, it has deleted one of these instances. As I change this guy to 4, it has deleted this instance. It has deleted one of them. So it's slowly draining. There's a rule that I applied here. It's called a disruption. So this disruption is actually telling it what parameters, what does it need to do. Yes, it can create more instances within the range of those limits. Yes, it can. Yes, it can. But because you have the ability to select something like spot instances or on demand, or optimize it to the instance type you want, it has that instead of having to manually check, oh, this is an AI workload, I need more compute here. Oh, this is just a CI/CD pipeline workflow. I don't need so much here. Oh, I don't need so much juice. Instead of having to create several node groups or node pools for several purposes, you just have this guy. And now this guy will be the one in charge of handling all of that stress. So as long as you define your YAML, your deployment correctly, you give your deployment the right amount of requests and limits if you want. You increase this to 1 gig or 2 gig, for example. It will select a different type of compute resource for you, because it's seen that this guy needs more compute than memory. So it feeds off of this guy to be smart enough to give you exactly what he wants. So it can create more instances. It can look for a bigger instance and save you cost. Instead of having 42 mediums, you can have one T3 large, for example. And you will see that, economies of scale is going to be cheaper using that big one. You know what they say, cheaper by the dozen, right? Get that big one instead of having to use several all over the place. So that is also an advantage of using Carpenter. So yeah, so this disruption here tells it that whenever this pod is underutilized or empty, give it 30 seconds before it kills it. I'm going to turn this guy to 0. Oh, I did not define this guy, this max queue. So this guy here, this guy is just saying, this topology spread restraint is just saying, oh, I don't want you to provision more than, so let's say you have 4 in 1A and 3 in 1B, that's fine. But the difference between the two zones should not be more than 1. So that's a way you're telling this guy to spread this deployment evenly across the zones. So this is where you define it. You define it in the actual deployment file, and then you list it from there. So that's why if you create several, I forgot to keep showing the zones. You're going to see that it's going to always, as long as there's more workload, it's going to try as much as possible to balance it, and the difference is not going to be more than 1. That way you're evenly spread across all the zones you want to work with. So let's change this guy to 0. Nothing. Yeah. So yeah. Yep. All right, guys. I think you can start asking questions now. I think, but after the demo, the next is Q&A. So, if there are any questions, you can put them in the chat. You can start answering questions now.
I think there are already a few in the chat. Um,
Okay.
yeah, Carpenter supports
So,
AWS primarily, but I think there is support for Azure coming out as well.
Azure. Yeah, there's support for Azure. There is for GCP, but it's still in beta. I won't advise to use it for production, but there's a repo that's being maintained by some people for GCP, but it's still in beta. It's still in testing. So you can, but it was predominantly made for AWS by AWS. So you know it's going to work better for AWS for now. So you can see I reduced this guy to zero. Let's say there was no traffic. We can see it has terminated the instance and just waiting for the next traffic to come before it start running. And that is how wonderful this guy can be. It's very efficient, very fast, and yeah. So for the questions in the chat, yeah, I've answered a few of them. Does it handle the amount of nodes? Yes. Noted. Can it create more instances? Yes. Is it for AWS? Yes and no. Somehow. All right.
Feel free to like unmute yourself and ask any questions. So I'm just going to wait a few more minutes, see if there's any more questions,
Okay.
and then you can call it a day.
Let me clean up this environment before AWS finishes my salary, before it comes. Okay. I've deleted all the 25 notes, guys. If you want to see it again, you have to run it on your own. You have to run it on your own environment. All right. So I don't think there are any questions. Oh, thank you, thank you, thank you. I think I have to go to I have to go to this.
Someone requested presenter mode. If you'd like to speak, you can just unmute yourself and go ahead.
Uh, okay.
Mm. All right then. In the absence, oh, hold on, one more. Okay. In the absence of any more questions, uh, oh, if it was self-hosted, that's interesting. Hmm. Possibly, like, I actually am not sure. It's a good question.
If what was self-hosted,
If the cluster was self-hosted, what would you use?
if the cluster was self-hosted, that's a very interesting question. So there is a
There's a
can't
slight
remember the
chance you might
name.
have to write your own like cluster autoscaler or
You
like
might have to
extend
write your
it.
own. Yeah. Um,
Yeah, because depending on how you do it, you'd need to like uh to inform the base cluster autoscaler how to provision a new node. And what a new node
you
looks
can
like would be very different depending on your environment.
set up.
So
Yeah,
the answer
you
to
would have
that is
a
I don't
job.
know, and you might have to write your own thing.
You must have a job. You must have a job in your. You must have maybe a job or something that pulls the a particular input, which is basically writing your own autoscaler, something that checks for
Yeah,
any sort of
exactly.
exactly. Then provision a new one.
Yeah, you do it in form of a Kubernetes controller. That's basically just tapping into the APIs and pulling events that are happening. And if a pod cannot be scheduled, or if the type of event is that the pod cannot be scheduled,
Sure.
you take
Yes.
that and then use it to provision a new node and then place that pod that's unable to be scheduled onto the new node. It's a bit involved, to be honest, but I'm sending a link in chat now to controllers.
Saying because Carpenter knows what nodes are available since
Yeah,
it
exactly.
tightly coupled. Yes, yes. So it has because of its tightly coupled, it has
Oh,
the ability to yeah. Sorry, do you want to say something?
oh no, sorry, someone was unable to speak, so you might be able to try now.
Oh, okay. Yeah, Michael, you could unmute.
Can you hear me now?
Yeah, we can.
Yes.
Oh,
Yeah.
super. I don't know what was happening. But yeah, so my question already entered it in the chat. Though your screen was tiny, I think you're using a Mac or something, but there's a logic to writing this particular script, right? I'm pretty much new to the whole DevOps platform engineering thing, but I was just wondering how you were able to write all those. Is there a logic to it, or you can just write it any which way you think fits? Hello?
Okay, you're asking
Hello?
if there is a logic
Yes, if
to
there's a
writing
logic
it.
to writing.
So
Um,
yeah, so there's a link that Jibril shared in the chat. So that's basically how you can create controllers. So it's going to be in form of like a YAML file. So it's going to be declarative. You
okay.
can check this link so that if there are ways you can write like controllers. So
Hmm.
this carpenter guy is sort of that as well. It's also like a controller. So it's going to run on the control plane and then monitor for events across the cluster. So you can use it's going to be very it's going to be YAML and it's going to be declarative. So you can look into this link to how you can write like custom controllers for your environment. So if you're self-hosting, that would be the way to go.
Okay. Thank you.
All right, thank you.
All right, last chance for questions. Anyone else? Okay, in the absence of questions, I would like to thank everyone for coming out and apologies for the delay in starting. But yeah, recordings will be available and I posted on the group chat. If anybody has any more questions, please feel free to drop them in the group. And thank you so much for joining in. Have a wonderful day. And thank you to OG for joining. Appreciate you taking the time.
Thank you everyone for joining. Thank you.
All right, then. Have a nice day, everyone. Bye.